Welcome to ViewChem, the chemistry animations channel. ZAITSEV'S rule of elimination. A reaction in which two atoms, or two groups of atoms, are removed from a molecule is called as elimination reaction. The removal of the atoms, or groups of atoms, may take place either from the same carbon atom, alpha elimination, or from adjacent carbon atoms, beta elimination, or 1,2 elimination, or from 1,3 carbon atoms, gamma elimination, or 1,3 elimination. A and B are the species that will be eliminated from the same carbon, that is, alpha carbon. It is an alpha elimination reaction. Please note that, in the general examples that are shown here, A is hydrogen, while B is nucleofuge, that is, leaving group. As a consequence of alpha elimination, carbene is formed. If the two species are eliminated from the adjacent carbons, that is, from alpha and beta carbons, then such elimination reaction is beta elimination. The result of beta elimination is formation of multiple bonds, that is, double or triple bonds. If the two species are eliminated from 1 and 3 carbons, that is, from alpha and gamma carbons, then such elimination reaction is gamma elimination. The result of gamma elimination is the formation of a 3-membered ring. Elimination reactions can take place either in the gas phase or in the solution. In the present animation video, mechanisms of elimination reactions that occur in solutions, particularly mechanisms of beta eliminations, specifically E1 and E2 eliminations, and ZAITSEV'S rule of elimination, are discussed. E2 elimination reactions. Elimination by molecular reactions. Primary alcoholides, on reaction with alcoholic KOH, the base, undergo dehydrohalogenation, that is, removal of hydrogen and halogen, to yield alkenes. Alkyl halide reacts with alcoholic KOH, that is, KOH dissolved in alcohol, giving potassium alkoxide, the base. Yields alkene. It is a second-order reaction. The rate of the reaction is directly proportional to the concentrations of the alkyl halide and the base. Mechanism of E2 elimination reactions. In E2 elimination reactions, elimination of hydrogen and the leaving group takes place simultaneously from the adjacent carbon atoms. It is a concerted reaction, that is, a single-step reaction. This reaction is an example of 1,2 elimination. To start with, potassium ethoxide, the base, interacts with hydrogen on the beta carbon to abstract it as H+ ion. As a result, the bonded pair of electrons of hydrogen and beta carbon polarizes between alpha and beta carbons, to form the double bond. In the process, leaving grouped parts with electron pair. The reaction proceeds through a transition state. In the transition state, beta carbon, hydrogen bond cleavage. Formation of bond between alpha and beta carbons. And cleavage of bond between alpha carbon and leaving group takes place. Alkene, the product, is formed from the transition state. In the E2 elimination reactions, all the 5 species, that is, base, hydrogen on the beta carbon, alpha carbon, and the bromine, should be in the same plane. The alkyl halide prefers anti-periplanar conformation, that is, a staggered, stable conformation. In the staggered conformation, hydrogen and bromine are in the trans disposition. Dihedral angle is 180 degrees, and are eliminated from the opposite sides. This type of elimination is anti-elimination. In the anti-elimination, formation of a stable, low-energy transition state is possible. This is because of effective overlap of orbitals and minimum repulsions between the base and leaving group. In the other possible elimination, the alkyl halide may assume syn-periplanar conformation, that is, an eclipsed, less stable conformation. In the eclipsed conformation, hydrogen and bromine are towards the same side. Dihedral angle is 0 degrees. Both hydrogen and bromine are eliminated from the same side. This type of elimination is syn elimination. In the syn elimination, transition state possess relatively more energy, hence less stable. The main reason for the lesser stability is higher magnitude of repulsions between the base and the leaving group, as both of them carry negative charge and are in close proximity. Energy profile diagram of E2 elimination reaction. The reactants have certain amount of energy. By acquiring free energy of activation, a transition state is reached. The rate of reaction depends on the activation energy. The difference in the energy of reactants and the transition state is activation energy. From the transition state, the products are formed. The difference between the energy of reactants and the products is free energy of the reaction. If the free energy change of a reaction is negative, that is, the energy of the products is less than the energy of the reactants, then the reaction is spontaneous, that is, exothermic reaction. E1, elimination reactions. Elimination, unimolecular, reactions. Tertiary alcoholides, on reaction with aqueous alcohol, a weak base, undergo dehydrohalogenation to yield alkenes. It is a first-order reaction. The rate of the reaction is directly proportional to the concentration of alkyl halide only. Mechanism of E1 elimination reactions. Due to higher electronegativity of halogen, the bonded pair of electrons of carbon-halogen bond are attracted towards halogen. As a result, partial positive and partial negative charges will be developed on carbon and halogen, respectively. E1 elimination reaction takes place in two steps. The first step in the mechanism of E1 elimination reaction is the ionization of alkyl halide to yield carbocation and halide ion. Formation of carbocation is slow and rate-determining step. It takes place through transition state 1. In the second step, base abstracts hydrogen as H+ ion from the beta carbon to yield the product, alkene. It is a faster step. This reaction proceeds through transition state 2. Energy profile diagram of E1 reaction. Cleavage of carbon-halogen bond will be initiated in the presence of polar solvent. As a result, transition state 1 will be formed, in which the process of bond breaking of carbon-halogen bond takes place. The activation energy, that is, the energy difference between the reactant, alkyl halide, and the transition state 1, is called delta G1. From the transition state 1, carbocation, with relatively lesser energy, is formed. In the second step, base abstracts hydrogen as H+ ion from the beta carbon to yield the product, alkene. It is a faster step. This reaction proceeds through transition state 2. The energy difference between the carbocation and the transition state 2 is delta G2. It is important to note that delta G1 is more than delta G2 because delta G1 is the slow and rate-determining step. From the transition state 2, the product with lesser energy than the reactant is formed. Secondary alcoholides may undergo either E2 or E1 elimination reactions, depending upon the reaction conditions. Following is the order of reactivities of alcoholides towards elimination reactions. In E2 elimination, tertiary alkyl halide is more reactive because greater the substitution on the alpha and beta carbons, more stable alkene is formed. In E1 elimination, tertiary alkyl halide is more reactive because greater the stability of carbocation, more stable alkene is formed. Further, please note that the reactivity of alkyl iodide is more than alkyl bromide, which is in turn more than alkyl chloride. Prior to the explanation of ZAITSEV'S rule, it is essential to know about vinylic and allylic hydrogens. Doubly bonded carbons, that is, sp2 carbons, are vinylic carbons. Hydrogens bonded to vinylic carbons are vinylic hydrogens. Those sp3 carbons that are bonded to vinylic carbons are allylic carbons. Hydrogens bonded to allylic carbons are allylic hydrogens. ZAITSEV'S rule. In the 1-2 elimination reactions, more heavily substituted alkene will be formed in the major proportion. Please understand the meaning of more heavily substituted alkene by observing the following examples. Unsubstituted alkene, monosubstituted alkene, disubstituted alkene, trisubstituted alkene, tetrasubstituted alkene. ZAITSEV'S rule can also be understood as: in most of the cases, in the 1-2 elimination reactions, the alkene that contains more number of allylic hydrogens will be formed in the major proportion. Let us consider the dehydrohalogenation of 2-bromobutane. If HA is eliminated, along with bromine, but-2-ene is the product. Alternatively, if HB is eliminated, along with bromine, but-1-ene is the product. But-2-ene contains 6 allylic hydrogens. Hence, 6 hyperconjugative structures are possible. But-1-ene contains 2 allylic hydrogens. Hence, 2 hyperconjugative structures are possible. But-2-ene is the major product because it is more heavily substituted compared to but-1-ene. Please note that more the number of hyperconjugative structures, more will be the stability. Hyperconjugative structures of but-2-ene. Six hyperconjugative structures of but-2-ene. Hyperconjugative structures of but-1-ene. Two hyperconjugative structures of but-1-ene. So, according to ZAITSEV'S rule, but-2-ene is more stable than but-1-ene. Comparison of E1 and E2 reactions. E1 is a unimolecular reaction, while E2 is a bimolecular reaction. In E1 reaction, the rate of the reaction depends on the concentration of alkyl halide only. But, in E2 reaction, the rate of the reaction depends on the concentrations of both alkyl halide and base. E1 reaction takes place in 2 steps. But E2 reaction takes place in 1 step only. In E1 reaction, formation of carbocation intermediate is the slow and rate-determining step. Elimination of H+ ion from the beta carbon gives alkene. E2 reaction involves a concerted mechanism in which departure of hydrogen and halogen takes place simultaneously from the adjacent carbons to yield alkene. The order of reactivities of alkyl in E1 reaction is in the following order: tertiary alkyl halide greater than secondary alkyl halide greater than primary alkyl halide. The order of reactivities of alkyl in the E2 reaction is also same as in E1 reaction. No specific geometry for alkyl halide is required. For E2 reaction to occur, hydrogen and bromine should be in the opposite sides, but in the same plane. That is, antiperiplanar conformation is preferred. Polar product solvents, like H2O, favor E1 reaction. Polar aprotic solvents, like dimethyl sulfoxide or dimethylformamide, favor E2 reaction. In E1 reaction, as the base has no role in the rate-determining step, weak bases can also be used. For E2 reaction, strong and bulky bases are preferred. Thanks for watching. Please like, share, and subscribe.